Today we're going to talk about what many mathematicians would say is one of their heroes, and that's Leonard Euler. He was a Swiss mathematician, mostly did his work in the early 1700s, so not too long after calculus was first formulated. You might remember that I told you his teacher was Johann Bernoulli, one of the famous Bernoulli family, and Euler went on to do things that surpassed what his teacher did, even though those were quite great in their own way. So one of the things Euler is attributed to is called Euler's method to approximate solutions to differential equations. So knowing that some differential equations can't actually be solved, Euler knew that it would be nice to have a method to approximate. So we've already talked about slope fields as one way of approximating, and this was just another one. So basically, a differential equation is something like dy dx equals some function of x and y. It could just be a function of x, and then it's usually easier to solve, but sometimes it's a function of x and y, and we usually have some kind of initial condition, like x sub 0, y sub 0 is on the solution. So say the solution we're really looking for is this curve, but we don't know that that's the solution. And we wanted to approximate another point over here. So the one thing we do know from a differential equation are slopes. So if we really wanted to try to approximate this curve, and we know it goes through this point, what might be a good idea is to take its slope. So if we took its slope, we would be getting a tangent line. And we could follow that tangent line until we got to that x value, and we could say that's our approximation. Now you might not think it's so great, but it's about the best we know because we have that slope there. So tangent lines do approximate curves. The biggest problem is the curves tend to change slopes. So Euler had the idea, well, if a tangent line is pretty good, how about if we take advantage that we know something about the slopes and do two tangent lines? Go from here about halfway, right here, follow the slope that far, and then readjust the slope. In other words, we can take this value of xy, put it into this differential equation, get a new slope. And the slope would actually be what it is right at this point. They wouldn't know that, but you could calculate that, and then you would follow that slope. And now your differential equation, you'd be approximating the solution to go through this point and this point and this point. So instead of one straight line, it would be two straight lines to make it even look a little bit more like this curve. And then we could, if that worked good, why not go to 4 tangent lines? So if you split it up here and here, we could follow the tangent line this far. Then we could readjust the slope by plugging this point into the differential equation and maybe getting something that looks like that. Then plugging that point in and readjusting the slope. And get another straight line, whoops, just up to here. And then readjust the slope again, seeing that the slope has gotten steeper, and go up to that point right there. Just get rid of that part that we didn't want. And now the round actual solution is being approximated by these 4 points, and we you can see that we're going to get a better approximation. So the more we do, the better it gets. So that was Euler's thought. He said, let's start out at the point x0, y0, and try to come up with a new point right here, x sub 1, y sub 1. So he said, let x sub 1 be where you started plus however far you go over right here. And that's the change in x. So say we call the change in x just h, from here to here. Then y sub 1 is going to be y sub 0 plus. Now, how do we get the new y value? You're going over this much, but then you're going up. You're following the slope. So the slope is the change in y over the change in x. So that means the change in y is the slope times the change in x. So h times the slope, and what would the slope be at this point, x0, y0? It'd be f of x0, y0. So the slope times the change in x gives the change in y, so that gives us our new y value. And then we repeat that process to get x sub 2 and y sub 2. We just keep changing these numbers. So the general method is x sub n plus 1 equals x sub n plus h. You're always just adding what h is to get to the new x value. And y sub n plus 1 equals y sub n plus h times the slope at that previous point. So n y sub n. Putting those two together, that is Euler's method for approximating the solution to a differential equation. It's what we call an iterative process. So you start out with n being 0, and you keep going through this process, and n equals 1, n equals 2, as many times as you want, as many times as you have the patience to do it. And I think right now you can see that this is something that would be done really nicely on a computer. It would be really easy to program this method. It's just a repetitive process, and that's what computers are good at doing accurately. So let's get into an example. So dy dx equals x over y. Y of 1 equals 2. So this is our initial condition, and we want to know what y of 3 is. So we start out with the point 1, 2. And I like to, instead of using Euler's method in this form, I like to just, in my head, know what it's doing and just put it into a chart. What are the things I need? I need the change in x. So it depends on how many steps we want to do. So on this first time, let's do it in 2 steps. So let's go from 1 to 3 in 2 steps. So that means the change in x is going to be 1. So that means if this was the first x, the next x is going to be 2. And then the next x is going to be 3, because the change in x is always 1. Now, we always need the slope. Where do we get the slope from? The differential equation. So in this case, x over y is 1/2. You can either do it in fractions or decimals. And then, this is the key. How do you get the change in y? It's the slope times the change in x. So 1/2 times 1 is 1/2, so this becomes 2.5. Maybe we should go to decimals. Then we have 2.5. We have x is 2 divided by 2.5, which is 20 divided by 25, or 0.8. And 0.8 times 1 is 0.8. That's the change in y. This was the old y, so the new y is 3.3. So we would approximate y of 3 to be approximately 3.3. Because this is kind of tedious, and I think it's pretty easy to see the method, I didn't want to have you watch me do all these, but I went through and did this with h being 1/2. So we do it in 4 steps. We go from 1 to 3, but each time the x changes by 0.5. And I think I did my calculations fairly accurately. You can just see the first one is the same. You still get 1/2, but now 1/2 times 1/2 is only 1/4. So instead of going to 2.5, we went to 2.25. And then we readjusted the slope. So as it turns out, then we say that y of 3 is approximately 3.39. And that should be a better answer. Now this is one we wouldn't have had to approximate. We can solve this separable differential equation. dy dx is a function of x and y, but I can separate them. So if I cross multiply, I get that, and then I take the antiderivative of both sides. I'm going to go through this fairly quickly because we've done a bunch of these before. Now we multiply everything by 2. Y squared equals x squared plus 2c, which we just call c. And then y is plus or minus the square root of x squared plus c. And then we put in our initial condition that 2 equals plus or minus the square root of 1 squared plus c. So c must be 3, and we must be using, since 2 is positive, we must be using the plus. So y equals the square root of x squared plus 3. So now that's the exact solution. So now I can say y of 3 equals the square root of, and if I put in 3, I get 9 plus 3, or 12. So that's the exact solution, which if you put on the calculator, you get approximately 3.46. And that would be the exact solution. You can see you were kind of getting there. Now, one reason that does such a good job, that if you graph that function there, forget about the 3 for a minute, the square root of x squared for positive values of x and y is just going to be like y equals x. It's a pretty much of a straight line. That 3 makes it slightly curved. But you can imagine the differential equations, approximations to them with tangent lines. If this is pretty straight, these tangent lines are going to do a better job of approximating. So you need less steps to do a good job. I think we did a pretty good job in just 2 steps. Okay, so let's go to another one. This time, y of 0 equals 1. And our slope equation is x plus y, our differential equation. And so say we do this in 2 steps. If we do this in 2 steps, from 0 to 3, well, actually, let's do it in 3 steps. So we'll go from 0 to 1 to 2 to 3. I think I need another section down here. So let's see. X plus y. So 0 plus 1 The slope would be 1. If we're doing this in 3 steps, then h is going to be 1. So the slope times the change in x gets the change in y, so this would become 2. It was 1 and you changed by 1. Now, what does the new slope become? X plus y would be 3. 3 times 1 is 3. So this was 2, it becomes 5. 2 plus 5 is 7. 7 times 1, 7. It was 5, it becomes 12. So we would say that y of 3 is approximately 12. But that's using fairly big steps. It worked pretty well in this one, but I have a feeling that this differential equation here is more curved. The solution to it is more curved. So what I did is I went through and did it with h instead of being 1, I did it with h equals 0.5. I did it by hand, and I came out with 18.78. Quite a bit different than 12. That's a good indication that this solution is going to be more curved. Well, I didn't do these by hand. I told you this would be really easy to do on a computer. So plugging in to Euler's method with h equals 0.1, it went up to 30. So you can see this is changing quite a bit. And then at 0.05, it went to 33, 35, at 0.001. So now I'm doing like 3,000 steps. I'm glad the computer's doing it. And it's 36.11. And then I went to 0.0001. So in 30,000 steps, it came out to be 36.17. So I bet you that is pretty accurate. Now, this is not just a function of x, and it's not separable. So this is one that you don't have to know how to do. But I thought I'd really like to know what this answer is. So let's just take a step into the future and do something from Calculus 4. Calculus 4 is all into solving differential equations, and that's where you'd learn to solve this. And it's something that still, I think you can follow just fine. So what we're going to do is let v equals x plus y. And then we're going to take the derivative dv dx. With respect to x, you get 1 plus dy dx. Well, dy dx is x plus y, which is v. So in place of dy dx, you could do v. So what was the whole purpose of that? Now we've got it in terms of v and x instead of y and x, but now it's separable. I can go dv over 1 plus v equals dx and take the antiderivative of both sides. And this is in the form of du over u, and this is just x plus c. Now given that 0, 1, v is going to be positive, because x plus y is equal to v, so I can drop the absolute value sign. I don't really need the absolute value sign. And now I can take e to both sides. If this equals this, then e to this power equals e to that power. And I get 1 plus v equals e to the x plus c, which is e to the x times e to the c, or just c e to the x. And then I could get v equals c e to the x minus 1. But we're really trying to solve for y. So in place of v, I'm going to put x plus y, and now I can solve for y. Y equals c e to the x minus 1. And now I can put in my initial condition. 1 equals c e to the 0 minus 0 minus 1. So c is going to equal 2. So your final solution is y equals 2e to the x minus 1. And with that, I now can plug in y of 3. And if you plug that into there, you get 36.171. So you can see that this is such a good solution, but you had to do an awful lot of iterations in order to make that work. You can see why the advent of the computer, Euler would be amazed to see this, because he would have been stuck to doing this and knowing that he didn't get a very good solution because the solutions were changing so much. And just to show you what this solution looks like, instead of actually graphing that out in the calculator, I did another method that we've done, slope fields. So if I plug a bunch of values in, this is what the slope field looks like. So if I take the initial condition at 0, 1, you can see the slope field is going to look something like that. So you can see this curve is really curving a lot, and that's why we had to take so many iterations. Okay, so let's progress to another one here. So, dy dx equals y over x. Y of 2 equals 2. So we're starting out at the point 2, 2. And what is the slope going to be? Y divided by x. 2 divided by 2 is 1. We're doing this in 3 steps. So we're going 2, and we're going to go up to 8. So 4, 6, I wasn't counting very well when I made my tables, 8. So if I'm doing that, if I'm going to 2 to 8 in 3 steps, my step size is going to be 2. I'm changing my x value by 2. 2 to 4 to 6 to 8. So the slope, 1 times the change in x gives the change in y, so this becomes, it was 2, it becomes 4. What's the slope going to be? 4 divided by 4 is 1. 1 times 2 is 2. So this becomes, what's 4? Becomes 6. 6 divided by 6 is 1. 1 times 2 is 2. 8. So we're going to say that y of 8 is approximately equal to 8. Now, what if in the initial condition, say the same differential equation, but the initial condition was y of 2 equals 4. Now, what would we approximate y of 8 to be? So, we're still going to make a step size of 2, but now when you look at the slope, y divided by x, 4 divided by 2 is 2. 2 times, we still have an h of 2, is 4. So 4 added to 4 gives you 8. Now you go 8 divided by 4 is 2. 2 times 2 is 4. 4 plus 8 is 12. 12 divided by 6 is 2. 2 times 2 is 4. 4 plus 12 is 16. So we would say that y of 8 is approximately 16. And can we actually solve this differential equation to see how good these might be? Well, this is separable. So I could go dy over y equals dx over x. And now, if I take the antiderivative of both sides, I get that. And now I want to take e to both sides. And this is going to be the absolute value of y. But again, we're talking about positive values of y, so I can just call it y. And this is e to the natural log of the absolute value of x times e to the c. And e to the c I can just call c, and e to the natural log of the absolute value of x I can call the absolute value of x, but we're dealing with positive x values, so I get y equals cx. So if I put in my initial condition, I get that c equals 1. So y equals x is the solution to this differential equation. Well, do you see why what is really then y of 8? It equals 8. Exactly what we predicted. And why did Euler's method do 100% correct? It's because the solution to that differential equation is a straight line. So tangent lines, no matter how many steps you take, are going to do perfectly. Now, what would be the only difference in this second one? It's the same differential equation, so I'd still get y equals cx, but now I would put in my initial condition of 2, 4, and I would get that c equals 2. So y equals 2x would be the solution to the differential equation with that other initial condition. And then I would say y of 8 is approximately equal to 16. Well, sorry, it's exactly equal to 16. We predicted that it would be 16. Again, the solutions are straight lines. Y equals 2x, y equals x. And just to show you, I showed you what a slope field would be like for y over x. I didn't show you all the points on here, but look what happens when you start at 2, 2. If you follow the slope field, you follow right along that straight line. If we started at the point 2, 4, right here, and followed the slope field, you'd get y equals 2x. You can see that unlike the other slope field we did, this slope field shows the solution to be straight lines. Okay, so I'm just going to do one other quick one just to show you that you don't have to go with positive values of change at x. You can go backwards. In other words, if y equals f of x is a solution to this differential equation with this initial condition, use Euler's method with 2 steps to approximate f of 0. Well, we know that f of 1 equals 2. And we want to find f of 0 in 2 steps. So what we're going to have to do is let the change in x be negative 1/2. So let's try it. Put the point 1, 2 into the differential equation. 4 minus 1 is 3. 3 times negative 1/2 is negative 3/2. So it was at 2, it's going down. You're just following the slope down now instead of up. So this is going to be 1/2. Now you go 2 times 1/2. 1 minus 1/2 is 1/2. And 1/2 times negative 1/2 is negative 1/4. It wasn't 1/2, so you would approximate that f of 0 is approximately 1/4. And that would be a pretty good approximation. I'm not going to try to solve. This is a non-separable one. I think you've seen enough how actual solutions go with the approximations that I don't have to show any more to you. So I think Euler's method isn't that hard. Euler was brilliant, but his method we can follow. It's just following tangent lines. And the more tangent lines you do, the better the approximation. So good. Have a good rest of your day.